Good afternoon, everyone, and welcome to tonight's event. So it's a great pleasure for me to introduce Stephen Hawking today. Stephen and I met in '97 in Cambridge, and I must say that when we first began to work together, it felt to me somewhat like I imagined listening to the Oracle of Delphi would be. At that time, what Stephen was telling me seemed as profound as it was difficult to decipher. Over the years, however, our discussions have grown more intense and we have developed a close collaboration that continues today. I am therefore deeply honored and especially delighted to have Stephen Hawking with us today in Paris. One of Stephen Hawking's principal research interests is the study of black holes. In 1974, Stephen Hawking showed that when one applies the laws of quantum mechanics to black holes, one finds that these thermally radiate and eventually evaporate. And this discovery led to the puzzle or paradox of what happens to all the information that falls into black holes. Hawking argued that this information would be lost forever when the black hole evaporates, and hence that the dynamics of black holes violates a fundamental axiom of quantum mechanics, namely that the total information is always preserved. Stephen Hawking's profound insight in the quantum nature of black holes, together with his insistency on a complete resolution of the black hole information problem, has forced us in the last decades to rethink the foundations of physics. Hawking's discovery has therefore been an enormous source of inspiration to the field of research. And in fact, this week, Hawking participates in a conference at the Institut Poincaré, devoted in particular to the black hole information paradox. Stephen once famously remarked that to confine our attention to terrestrial matters would limit the human spirit. And in his lecture today, which is entitled "Why We Should Go into Space," Hawking will elaborate on this theme. And indeed, Hawking views our research in the sciences very much within this broader perspective. And I know, in fact, of no one else in the world who can convey this message in a more inspiring and forceful manner. Ladies and gentlemen, please welcome a most distinguished colleague and friend, the Lucasian Professor of Mathematics of the University of Cambridge, Stephen Hawking.
Why should we go into space? What is the justification for spending all that effort and money on getting a few lumps of moon rock? Aren't there better causes here on Earth? In a way, the situation is like that in Europe before 1492. People might well have argued that it was a waste of money to send Columbus on a wild goose chase. Yet the discovery of the New World made a profound difference to the old. Just think, we wouldn't have had a Big Mac or KFC. Spreading out into space will have an even greater effect. It will completely change the future of the human race and maybe determine whether we have any future at all. It won't solve any of our immediate problems on planet Earth, but it will give us a new perspective on them and cause us to look outwards rather than inwards. Hopefully, it will unite us to face a common challenge. This would be a long-term strategy, and by long-term, I mean hundreds, or even thousands of years. We could have a base on the moon within 30 years, reach Mars in 50 years, and explore the moons of the outer planets in 200 years. By reach, I mean with manned, or should I say, person space flight. We have already driven rovers on Mars, and landed a probe on Titan, a moon of Saturn, but if one is considering the future of the human race, we have to go there ourselves. Going into space won't be cheap, but it would take only a small proportion of world resources. NASA's budget has remained roughly constant in real terms since the time of the Apollo landings, but it has decreased from 0.3% of US GDP in 1970 to 0.12% now. Even if we were to increase the international budget 20 times, to make a serious effort to go into space, it would only be a small fraction of world GDP. There will be those who argue that it would be better to spend our money solving the problems of this planet, like climate change and pollution, rather than wasting it on a possibly fruitless search for a new planet. I am not denying the importance of fighting climate change and global warming, but we can do that, and still spare 0.25% of world GDP for space. Isn't our future worth 0.25%? We thought space was worth a big effort in the 60s. In 1962, President Kennedy committed the U.S. to landing a man on the moon by the end of the decade. This was achieved just in time by the Apollo 11 mission in 1969. The space race helped to create a fascination with science, and led to great advances in technology, including the first large-scale integrated circuits, which are the basis of all modern computers. However, after the last moon landing in 1972, with no future plans for further manned space flight, public interest in space declined. This went along with the general disenchantment with science in the West, because although it had brought great benefits, it had not solved the social problems that increasingly occupied public attention. A new manned space flight program would do a lot to restore public enthusiasm for space, and for science generally. Robotic missions are much cheaper, and may provide more scientific information, but they don't catch the public imagination in the same way. And they don't spread the human race into space, which I'm arguing should be our long-term strategy. The goal of a base on the moon by 2020, and of a manned landing on Mars by 2025, would reignite the space program, and give it a sense of purpose, in the same way that President Kennedy's moon target did in the 1960s. A new interest in space would also increase the public standing of science generally. The low esteem in which science and scientists are held is having serious consequences. We live in a society that is increasingly governed by science and technology, yet fewer and fewer young people want to go into science. A new and ambitious space program would excite the young and stimulate them to go into a wide range of sciences, not just astrophysics and space science. A high proportion of today's scientists say their interest in science was sparked by watching the moon landings. What will we find when we go into space? Is there alien life out there, or are we alone in the universe? We believe that life arose spontaneously on the Earth, so it must be possible for life to appear on other suitable planets, of which there seem to be a large number in the galaxy. But we don't know how life first appeared. The probability of something as complicated as a DNA molecule being formed by random collisions of atoms in the primeval ocean is incredibly small. However, there might have been some simpler macromolecule, which then built up to DNA, or some other macromolecule capable of reproducing itself. Still, even if the probability of life appearing on a suitable planet is very small, since the universe is infinite, life would have appeared somewhere. If the probability is very low, the distance between two independent occurrences of life would be very large. However, there is a possibility known as panspermia, that life could spread from planet to planet, or from stellar system to stellar system, carried on meteors. We know that Earth has been hit by meteors that came from Mars, and others may have come from further afield. We have no evidence that any meteors carried life, but it remains a possibility. An important feature of life spread by panspermia is that it would have the same basis, which would be DNA, for life in the neighborhood of the Earth. On the other hand, an independent occurrence of life would be extremely unlikely to be DNA-based. So watch out if you meet an alien. You could be infected with a disease against which you have no resistance. One piece of observational evidence on the probability of life appearing is that we have fossils of algae from 3.5 billion years ago. The Earth was formed 4.6 billion years ago, and was probably too hot for about the first half billion years. So life appeared on Earth within half a billion years of it being possible, which is short compared to the 10 billion year lifetime of an Earth-like planet. This would suggest either panspermia, or that the probability of life appearing independently is reasonably high. If it was very low, one would have expected it to take most of the 10 billion years available. If it is panspermia, any life in the solar system, or in nearby stellar systems, will also be DNA-based. While there may be primitive life in our region of the galaxy, there don't seem to be any advanced intelligent beings. We don't appear to have been visited by aliens. I am discounting reports of UFOs. Why would they appear only to cranks and weirdos? If there is a government conspiracy to suppress the reports, and keep for itself the scientific knowledge the aliens bring, it seems to have been a singularly ineffective policy so far. Furthermore, despite an extensive search by the SETI project, we haven't heard any alien television quiz shows. This probably indicates that there are no alien civilizations, at our stage of development, within a radius of a few hundred light years. Issuing an insurance policy against abduction by aliens seems a pretty safe bet. Why haven't we heard from anyone out there? One view is expressed in this Calvin cartoon. The caption reads, "Sometimes, I think that the surest sign that intelligent life exists elsewhere in the universe is that none of it has tried to contact us." More seriously, there could be three possible explanations of why we haven't heard from aliens. First, it may be that the probability of primitive life appearing on a suitable planet is very low. Second, the probability of primitive life appearing may be reasonably high, but the probability of that life developing intelligence like ours may be very low. Just because evolution led to intelligence in our case, we shouldn't assume that intelligence is an inevitable consequence of Darwinian natural selection. It is not clear that intelligence confers a long-term survival advantage. Bacteria and insects will survive quite happily, even if our so-called intelligence leads us to destroy ourselves. This is the third possibility. Life appears, and in some cases, develops into intelligent beings. But when it reaches the stage of sending radio signals, it will also have the technology to make nuclear bombs and other weapons of mass destruction. It would therefore be in danger of destroying itself before long. Let's hope this is not a reason we have not heard from anyone. Personally, I favor the second possibility, that primitive life is relatively common, but that intelligent life is very rare. Some would say it has yet to occur on Earth. Can we exist for a long time away from the Earth? Our experience with the ISS, the International Space Station, shows that it is possible for human beings to survive for many months away from planet Earth. However, the zero gravity of orbit causes a number of undesirable physiological changes, and weakening of the bones, as well as creating practical problems with liquids, etc. One would therefore want any long-term base for human beings to be on a planet or moon. By digging into the surface, one would get thermal insulation and protection from meteors and cosmic rays. The planet or moon could also serve as a source of the raw materials that would be needed if the extraterrestrial community was to be self-sustaining, independently of Earth. What are the possible sites of a human colony in the solar system? The most obvious is the moon. It is close by and relatively easy to reach. We have already landed on it and driven across it in a buggy. On the other hand, the moon is small and without atmosphere or a magnetic field to deflect the solar radiation particles, like on Earth. There is no liquid water, but there may be ice in the craters, at the north and south poles. A colony on the moon could use this as a source of oxygen, with power provided by nuclear energy or solar panels. The moon could be a base for travel to the rest of the solar system. Mars is the obvious next target. It is half as far again as the Earth from the Sun, and so receives half the warmth. It once had a magnetic field, but it decayed 4 billion years ago, leaving Mars without protection from solar radiation. This stripped Mars of most of its atmosphere, leaving it with only 1% of the pressure of the Earth's atmosphere. However, the pressure must have been higher in the past, because we see what appear to be runoff channels, and dried up lakes. Liquid water cannot exist on Mars now. It would vaporize in the near vacuum. This suggests that Mars had a warm wet period, during which life might have appeared, either spontaneously or through panspermia. There is no sign of life on Mars now, but if we found evidence that life had once existed, it would indicate that the probability of life developing on yes. NASA has sent a large number of spacecraft to Mars, starting with Mariner 4 in 1964. It has surveyed the planet with a number of orbiters, the latest being the Mars Reconnaissance Orbiter. These orbiters have revealed deep gullies and the highest mountains in the solar system. NASA has also landed a number of probes on the surface of Mars, most recently, the two Mars rovers. These have sent back pictures of a dry desert landscape. However, there is a large quantity of water in the form of ice in the polar regions. A colony on Mars could use this as a source of oxygen. There has been volcanic activity on Mars. This would have brought minerals and metals to the surface, which a colony could use. The Moon and Mars are the most suitable sites for space colonies in the solar system. Mercury and Venus are too hot, while Jupiter and Saturn are gas giants, with no solid surface. The moons of Mars are very small, and have no advantages over Mars itself. Some of the moons of Jupiter and Saturn might be possible. In particular, Titan, the moon of Saturn, is larger and more massive than our moon, and has a dense atmosphere. The Cassini-Huygens mission of NASA and ESA has landed a probe on Titan, which has sent back pictures of the surface. However, it is very cold, being so far from the sun, and I wouldn't fancy living next to a lake of liquid methane. What about beyond the solar system? Our observations indicate that a significant fraction of stars have planets around them. So far, we can detect only giant planets, like Jupiter and Saturn, but it is reasonable to assume that they will be accompanied by smaller, Earth-like planets. Some of these will lie in the Goldilocks zone, where the distance from the star is in the right range for liquid water to exist on their surface. There are around 1,000 stars within 30 light years of Earth. If 1% of these had Earth-sized planets in the Goldilocks zone, we have 10 candidate new worlds. We can't envisage visiting them with current technology, but we should make interstellar travel a long-term aim. By long-term, I mean over the next 200 to 500 years. The human race has existed as a separate species for about 2 million years. Civilization began about 10,000 years ago, and the rate of development has been steadily increasing. If the human race is to continue for another million years, we will have to boldly go where no one has gone before. Thank you for listening.
I think that we now have the technology and we should invest more money on that, and maybe we can, the technology we have nowadays, go to other planets, or we still have to discover some new technologies to go there.
We don't yet have the technology, but we can develop it over the next 200 years while we explore the solar system.
So this is just a simple yes or no question. You've mentioned yourself during your speech that we could risk perhaps being contaminated if we ever met some sort of extraterrestrial life form. You also know probably that when explorers got to America, they brought with them viruses that decimated local Native American tribes. So this is the question. Do you think that if right now we found some life form, extraterrestrial life form, we know it exists, do you think it is wise for us to interact with them directly and risk either contaminating them or them contaminating us with something dangerous? Do you think the risk is worthwhile?
I think we have to be very careful. If we find life on Mars, we shouldn't bring it back here.
If any other extraterrestrial life exists, do you think they are ahead of us?
If there is more advanced civilization, why haven't we heard their radio signals? I think there can only be primitive life.
So this is the core of Stephen's argument, right? The fact that we haven't seen or heard from extraterrestrial intelligent life poses a puzzle. And so either it has to be rare, or it has to have a very small chance of sustaining itself. So that is the puzzle which leads, or which is one of the motivations, I think, to go into space. So I think we should perhaps leave it here, or...
Yes.
Okay, so let's thank Stephen again.